Welcome to part 2 of exponential and logarithmic functions, an overview. We're into the definition and introduction of logarithmic functions, called log functions for short. Now, it's really critical that you remember that logs undo exponential functions. Remember, exponentials mean that there's a variable in the exponent, and if I want to figure out what that variable is, the example I gave previously was 2 to the x equals 5, and I say, what is that x? What we need to remember is that this, again, is a transcendental function. You have to use something besides what you normally know in algebra to solve this problem. You have to use logs, because logs give powers. And that's the bottom line. That if you remember that, it should help you set up your logs equations and remember when you're using them. Logs give powers. This is really important. So we use logs to solve equations where we need to get a variable out of the exponent. Okay? So in the situation of 2 to the x equals 5, you cannot solve this equation without logs. So the definition of a log, if I have something that looks like this, an exponential, x equals b to the y, and I want to figure out the exponent, the y, I would rewrite it. And I start at the exponent, and then I do a loop to here. I end there. So I say the exponent, come over to my logs here on the left, so the exponent equals log to the same base with the argument being x. So the base is a little subscript in the logs. The x is what your exponential function equaled, and your y is your power. Okay, y is the power. This is what we want. This is the piece we're trying to find. So if we don't know powers, we can rewrite it as a log, and then we'll know what x is. So the question you ask yourself when you see a log is you say, the base raised to what power is equal to the argument? And I'll show you a bunch of examples for that, and you might want to write this down very large in your notes. Remember, logs give powers. Power equals log to the same base. Remember, this is a subscript, the base of the argument. We're going to do a bunch of examples on the next slide, but you really want to make sure you write down this is the fundamental definition of logs. If I have x equals b to the y, I can rewrite it as y equal to log base b of x. Put that at the top of your page, put a big box around it, a square, star it, whatever you need to make sure you have that down. Okay, so let's just do some straight converting. Remember, we're going to start at the power, and then we're going to make a loop. So we start at the 3, and then we make a loop down and around. My pen is not working so great. So I start at the 3, and I say 3 equals. I have it written over here off to the right. So 3 equals log base 2 of 10 to the n. You start at the n, and you say n equals log base 10 of 100. And the last one, you say 2 equals log base p of 25. So, we'll do some more. Then, if it has a base of 10, it has a special name, and the special name is called common log, which means it's used a lot. And anytime you see a common log, it's always written without the 10 there. So log base 10 of 100, you will see, is written simply as the log of 100 without the 10. The 10 is understood in the common log. Now to convert from logs to exponents, the base raised to what power is equal to the argument. So this time, we're going to start at the base. When we're converting to logs, we start at the exponent and we loop. When we're converting from logs, we start at the base and we loop. So here, log base 2 of 16 equals x. I'm saying 2 raised to what power is equal to 16? A raised to the negative 2 is equal to 1/4. So can I figure out what A is? 5 squared is equal to y. So I can figure out what y is. What about this one? There's no base here. Oh, that's right. This is a common log. So there's a 10 understood there. So 10 cubed is equal to x. All right? So notice for these last two, the x and the y were the argument. So if I have a log and I don't know what the argument is, I write it as an exponential, because then I know that the argument was 25 and the argument is 1,000. All right, so let's talk a little bit more about common logs. If I have 10 to the n equals 100, what's n? You know? Hopefully you do. So I'm not going to tell you. Let's convert it into a logarithmic equation. Remember, start at the n, loop around, n equals log base 10 of 100. Right? So now you can remember the question you ask whenever you have a log. 10 raised to what power equals 100? 10 raised to what power equals 100? So either case, you get n equals 2. 10 raised to the second power equals 100. Now go to your calculator and find the button that says log. Everyone's got it on their calculator somewhere. Look around, look all over on yours. I'll show you where it is on a TI-84 right here. Okay, so here's a screen calculator emulator of the TI-84 Plus. You can actually get this for free on the internet. It's a little bit tricky to install, but I can help you with it, or you can read me and figure it out. It's called WABBIT, EMU, WABBITEMU. So if you don't have a graphing calculator and you want to use one on your computer, this is a good one. Anyway, so the log button on this calculator is right here, log. So I type log 100. Always close the parentheses on your calculator, and the answer is 2. Because remember, 10 raised to what power is 100? The answer is 2. Logs give you powers. So let's keep going back here. So again, the 10 is understood. Calculators calculate logarithms directly only when they are base 10. So if I ask you what is the log base 2 of something, you cannot just type it into your calculator. Now, think about this for a second. Log base 10 equals 1. Log of 10 equals 1. So what's the base here? It's 10. 10 raised to what power equals 10? Obviously, it's 1. 10 to the first power is 10. Since 10 and 10, anytime the base and the argument match, the answer is always 1. Because the base raised to what power gives the same number, it's always going to be 1. Okay, so now we have another special kind of logarithm, and that is called a natural log, and these are used a lot. There's a lot of applications that we will do that use natural logarithms, and these are probably even more common than common logs. So first of all, can you figure this one out? You don't need a calculator. E to the x equals 1. What does x have to be if it's equal to 1? So pause it if you need to really think about it. All right, again, I'm not going to tell you for a second, so let's convert it. The x equals log base e of 1. Now, on your calculator, you want to find the ln button. So it might look like 1n, it's ln, and we're going to calculate ln of 1. I'll show that as well. So the ln button is on the calculator, the TI-84, directly under the log button. It's capital L, so it's not confusing. So ln of 1, hopefully you figured this out, it's 0. Because anything raised to the 0 power is going to be 1. Okay, so notice that log base e, I'm saying, is the same as ln. It is. Ln stands for natural log. Anytime I have a log that is base e, it is called a natural log, and we never, ever write log base e. Instead, you use the letters ln. So I would never write log base e. I would always write this as ln1. And notice I did the L as a cursive L, and that's so it's not confusing whether it's a L or a 1. So you see most mathematicians write the L as a cursive L. Now, if you want to do a little practice, again, remember, we're thinking for logs, the base raised to what power is equal to the argument. So here I have the base e raised to the what to the first power gives me e. So natural log of e is always 1. You can practice this if you want in your calculators, just to practice, but it's not necessary. Okay, calculating logs by hand. Again, it's important to ask yourself the question, the base raised to what power equals the argument? 5 raised to what power is going to equal 25? 2, right? What is the log of 1,000? Again, we don't know what the base is. The base is 10. Base is 10 if there's no base written out and the word is log. So I say 10 raised to what power is 1,000? And 10 cubed is 1,000, so the answer is 3, because logs give powers. Remember that. I'll write it again just to make sure you remember. Logs give powers. Now, notice I never have the word log all by itself. It's always the log of something, because the example I give is if I have the square root of 5. This is the square root of 5. You would never, ever divide by the square root and tell me that equals 5, right? This is a big no. I'm going to change the color of the pointer and just say that really quickly, that you never ever do this, right? Because the square root is doing something to the 5. It's operating on the 5. So, in that same way, it is critical to pay attention when we're doing logs. If I have the log of 100, you do not divide by log and tell me equals 100. This, again, let me change the color, is a giant no. Okay? Never, ever separate the word log from the argument. The 100 is the argument, because we know the log of 100 is actually 2. 10 raised to what power is 100? So log of 100 is actually equal to 2. Never, ever, ever take the word away from the numbers. I cannot stress that enough. So that is a major problem of novice logarithmic function users. All right, what is the natural log of 1? Remember, you never say what is ln1. That's you always say what is the natural log. You always say the words. Now remember that ln has a base of e, so I'm saying e raised to what power is 1. And we did that on the previous slide. Again, logs give us powers. Anything raised to the 0 power gives us 1. Now what happens if you don't have a log that is base 10 or base e, like this one, log base 4 of 64? Now, we can figure out this one by hand. 4 raised to what power gives us 64? 4 raised to what power gives us 64? 4 times 4 is 16. 16 times 4 is 64, so I know it's 3. But if I went to my calculator right now And let's do that. Let's see what happens if we type log 64. Okay, so let's try saying log of 64. See what we get. Whoa, that's not 3. What if we said log of 4? Does that work? No. What if we said log of 4 times 64? Does that work? No. None of those is going to give us 3. So there's an actual special formula that we have to do. It's called the change of base formula. So we just did method of 1. 4 raised to what power is 64? So we know it's 3. Now the method 2 is the change of base formula. Now also in the student Google Drive folder, I have a list of log properties, and this is one of the properties on that list. You should make sure you print that out and have that with you also for this whole section. It's really important. You're also going to probably want to copy some of those properties down on your sheet of notes for the final. So the change of base formula says if I have a log of any base with m as an argument, I can rewrite it as a log of a totally different base with the same argument divided by log of a totally different base of the base a. So this is a little bit confusing because people in general don't have it equal log of just any base. They have it equal the log base 10. So it's the log of m over the log of a. Or they have it equal the natural log, which is log base e over the natural log. Now, believe it or not, both of these two will give you the same answer. So if I rewrite log base 4, oh, this was supposed to be 64. Sorry, we're going to do 64, not 16. So let's go back to our calculator and try using the change of base formula. So we're going to do log of 64, close parentheses, divided by log of 4, and we should get 3, right? Let's see if we do. 3. Now remember I said it's really important to close your parentheses? Watch what happens if I don't close my parentheses. I just do log 64 divided by log of 4 because I'm in this big hurry. I do not get the right answer because it moves the log inside the argument of the first log. So please, 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 always close parentheses. All right, so let's try with natural log and see if I also get 3. Natural log of 64 divided by the natural log of 4. And yes, I do get 3. So why don't you try it yourself with log of 16 over log 4, and hopefully you know 4 raised to what power is 16, so you know the answer to that should be 2. And then if you want to do a couple more, here's a couple more. Okay, so I'm not really spending tons of time on the graphing on this, but I did want to point out that the log function is the red here, and it is the inverse of the exponential function. Now, inverse functions mean swap x and y. Okay, that's what it means to be an inverse. The big idea, in a nutshell, for inverse, and I'll just write that on here, is swap x and y. So, if I go in and take this point right here, and that point is x is 0, y is 1, then this other function has x and y swapped. X is 1, y is 0. Okay? So any point on this curve, if you swap x and y, you will get the point on this curve. That's what makes them inverses. So the graph of a log function is the one you just saw here. And then that's if the base is a whole number. If the base is a fraction, it looks like that. And the domain and the range are swapped from the domain and the range of an exponential. So I'm actually going to pause, and we will go into the fundamental properties of logs in the next part.